part is okay. So my sort of to give you an idea about my current research interest. So I told you about photon-photon interactions, quantum optics. So I really started out as as using solid state media as a means of studying quantum optics, and where I am now is the other way around. So I'm using quantum optical techniques to study strongly correlated states in condensed matter. So so that's what I would like to sort of tell you about. So I do so be in my group. We do so primarily using 2D materials, and I think you might have heard about these materials. They're outstanding scientists at Harvard, MIT, and all around the world. Working with these, and the idea is this: that there is a very large family of materials. The last number I know is more than 5,000, which actually have very strong bonds between atoms in the plane and weak van der Waals bonds that connect different layers. So these layered or two-dimensional materials have this fantastic property that one can use rather mundane ways like Scotch tape to basically exfoliate materials down to a single atom thick layer. And then once you do that, you can then stack them up like you do in Lego and bring together materials with very different properties. It could be a Dirac semi-metal like graphene. It could be an insulating material like boron nitride. Could be semiconductor materials, etc. Right? So this is has become over the last, I would say, 10 years a completely new playground for investigating many body physics in the solid state. So one interest in this material system is that one can control the charge density via gates. So one can basically keep the material neutral or change the charge density to relatively large values of 10 to the 13 per centimeter square, etc. And the mass of the carriers can be relatively heavy. So the net effect of this is that if you look at the ratio of the characteristic interaction Coulomb energy between electrons, and if you then compare this to the characteristic kinetic energy of electrons, this ratio can become extremely large. So it's quantified or designated as the RS parameter. And in typical materials, this number is on the order of 1. And in the 2D materials, one can easily get to a point where it can be larger than 30. So what is nice about this is that if kinetic energy dominates, that means that the properties of electrons in the system can be described in terms of the properties of a single particle. Whereas if the Coulomb energy dominates, then the electrons tend to develop strong correlations, or the material can become strongly entangled. And the net result is that you can obtain behavior that you may not be able to easily calculate or predict ahead of time. So another aspect of these materials is that when you're stacking them on top of each other, you can introduce a twist angle. And this twist angle allows you to realize a superlattice and a so-called flat band. So I don't want to go too much into this. I just want to flash some recent results, which again, I imagine many of you have learned about, which is this, if you take two graphene layers and instead of putting them directly on top of each other, if you introduce a slight angle, then you basically create a periodic potential for the electrons. And these define new bands which can be very flat. That is the width of these bands could be on the order of 5-10 milli-electron volts. So the bottom line is here that you can start out with 2 layers of graphene, which are semi-metals. They're interesting, but let's say not very exotic. And once you bring them, combine them with the small angle, then you get something extremely exotic that as you change the charge density, you can render it, taking it from a band insulator to a correlated insulator to a superconductor and so on. So all within the same material and just by changing the applied gate voltage. Okay, so this basically, I guess, has really captured the imagination of the condensed matter physics community over the last 3 years since Pablo Jarillo Herrero at MIT first demonstrated this effect. Now, so one question that we have been interested in is whether such twists and superlattice potentials are really necessary to observe the effects of strong electronic correlations. Okay, so I defined for you the RS parameter already, the ratio of the Coulomb to kinetic energy, and this has an interesting dependence that the kinetic energy, as you know, increases with the momentum squared. So that actually is proportional to the density of electrons, density of fermions. So the higher the density, then the higher the characteristic kinetic energy of the electrons would be. And this is linearly proportional. Now, if you look at the Coulomb energy, that goes as 1 over r, as you know. So therefore, if you increase the density, the Coulomb interaction, characteristic Coulomb interaction energy will increase with the square root of the density. So what that says is that if density is high, RS parameter will eventually become very small because of this linear dependence of the kinetic energy. And in this case, we have still something interesting, but something that we understand well. The Fermi liquid or the electrons can be described as forming a liquid. Okay. Now, the counterintuitive part is that as you reduce the density, you increase the separation of the electrons, so you reduce the Coulomb interaction. But since you reduce the relevant kinetic energy more, you can actually go to a new state of matter, which was predicted by Eugene Wigner about 87 years ago. So basically the prediction is indeed, if this ratio is very large, it's favorable for electrons to form a lattice, spontaneously break translation symmetry, and thereby minimize the Coulomb interaction or Coulomb repulsion between them. And they do so despite the fact that being localized costs them kinetic energy. So if the Coulomb interactions are very strong, this becomes an energetically favored state. So this is, of course, it's a long story, and it's a one can say that it's one of the sort of the long-lasting predictions of condensed matter physics. So there have been investigations of Wigner crystals, primarily in gallium arsenide, which really has a lousy RS parameter of order 1. People have found ways to go around this by applying magnetic field to force electrons into lambda levels. And once electrons are in a lambda level, their kinetic energy is quenched, and then they could develop a Wigner crystal. Now, but all these experiments basically provided indirect evidence for an Wigner crystal. So basically, as you can see here, that you measure a resistivity or resistance, and around these fractional quantum Hall effects, which I will not go into, people have seen that there are regions with particularly below, at very low densities, very high resistance. So these are consistent with the existence of a Wigner crystal, but really doesn't tell us anything about the periodic ordering of the charges. And that's what we set out to show, that we wanted to see if we can get to a regime and use our, let's say, knowledge of optics to basically get a direct evidence for the periodic ordering of charges. Okay, so to this end, we went to 2D materials. I already mentioned the advantage of a two-dimensional material, that the RS parameter could be rather large. So the material of choice are these 2D materials called transition metal dichalcogenides, which are semiconductors. And they are actually a monolayer of a transition metal dichalcogenide consists of 3 layers, a metallic layer of transition metal like molybdenum sandwiched in between 2 layers, triangular lattices of chalcogenide, in our case, selenium. So basically, this is our, let's say, workhorse. What we do is that we make a heterostructure by exfoliation, and in our case, it's the simplest possible heterostructure. So this purple region is a monolayer of molybdenum diselenide. It is sandwiched in between boron nitride layers, about 50 nanometers thick. And then as gates, we use another 2D material, which is graphene. So it's all 2D Scotch tape fabrication that allows you to put together the structure you're interested in. Of course, you need electrical contacts. For this, you need E-beam, deposit these gold contacts. And now you have, and this is the picture of a real device, then you now have a real device where you can do experiments, either electrical or optical investigation. So now I should say a bit more about our optical investigation, because it involves not only electrons in this 2-dimensional material, but also excitations, which we refer to as excitons. So first on electrons, so because using this top and bottom gates, we can actually, this is a capacitor device, we can control the charge density, free charge density, electron or hole density in this semiconductor. So that's a standard tool in this field. Now, by using resonant lasers, we could inject another kind of quasi-particles, and these are neutral excitons. And an exciton is a bound state of an electron to a positively charged hole, and it's similar to, in many ways, to a positronium, albeit with a much smaller energy of the photon upon recombination. So the idea is this: we can think of a conduction band. We can have free electrons here, but we can also use a photon to excite an electron from the valence band to the conduction band. And particularly in these 2D materials, the electron that you excite remembers the hole that it has left behind in the valence band and sticks to it. So in that sense, forms this bound state to the hole that it has left behind. So its position is correlated with the missing electron in the valence band. Okay, so that's probably the best description I can give of an exciton. And when you now look at the spectrum, so this is a color-coded map, the reflectance or the optical reflectivity is coded in colors. So when there are no charges, we see this nice exciton resonance, and when we inject electrons, then we see that the spectrum gets modified. And we do not need to worry too much about understanding these modifications, but hopefully that it won't be necessary. Okay, so now hopefully I gave you a feeling for what excitons are. These are now both quasi-particles. We can just forget about the fact that exciton actually consists of an electron and hole. It's a neutral particle, and it's a bosonic particle, but it has a finite mass, so therefore its energy increases quadratically with its momentum, and so does for the electrons. Okay, so we call this a parabolic dispersion, describing the particles which in the absence of an external potential. Now, the nice thing here is that unlike photons and electrons, which interact very weakly, excitons and electrons can interact rather strongly, because exciton is a dipole and electron has a charge, and the dipole charge coupling can be relatively strong. So you see what we've done is that we take a photon, which is a neutral particle, but doesn't really interact with electrons. But when we convert it into an exciton, a polarization wave, one can also think about it in this way, then the interactions with electrons can become much stronger. So that allows us to study, and you can see that here, the presence of electrons, and more than that, the state of electrons. So you can see this increase in energy of the exciton is due to its interaction with the electrons. So what happens now? So we have an undoped system. We have this parabolic dispersion for the excitons. Now we inject the electrons, and if these electrons are in a liquid state, then what happens is that this repulsive interactions blue shift the exciton resonance. The dispersion curve does not get modified. But if the electrons by lowering the temperature, if we can bring them into a Wigner crystal state, then things change dramatically, because now the excitons no longer see a translational invariant system. They interact with the electrons, and since electrons form this periodic lattice, now the excitons see or are subject to a periodic lattice, and that modifies their dispersion relation. And this one can understand through a Bragg-Umklapp scattering of the excitons. And what is really important is that in reality, even though the span diagram is relatively complex in 2 dimensions, what is important is that in the absence of periodic ordering, we only have the basic exciton line. Now we start to see in the light cone new excitonic resonances that only exist due to the presence of a periodic charge distribution. So I don't want to prolong this very much. I just want to show you the data. So this is, again, the excitonic spectrum as we introduce electrons into the system. And this is where we want to focus. And what we see when we focus well is that in addition to this exciton resonance, there's a new resonance that is blue shifting from the exciton as we increase the density. And the reason for the blue shift is that as we increase the electron density, the Wigner crystals, the electron separation of electrons is becoming smaller, and that corresponds to a higher lattice momentum, which in turn results in a higher energy of the exciton. And this agrees very well with our expectations in the system. And what we claim is that now the presence of this resonance is a direct evidence for the existence of periodic order. And we can melt it by increasing the temperature. So I show you data at 80 millikelvin here. Up to 4 Kelvin, not much of a change happens. It's a bit broader, but as you go through 10 Kelvin, this additional resonance, it disappears because electrons are no longer forming this crystalline state, but they melt into a liquid state. And how this transition occurs is really not understood, not even theoretically, and that's what we intend to study in the future. So that's where I will stop the scientific part.
We'll take any questions from the audience at this time, and you can raise your hand and go ahead and ask.
So maybe I'll go really quickly. Okay. Oh, Will, go ahead, please.
Go ahead.
Hi, I really enjoyed your talk, and I was just wondering, at the end when you're talking about the Umklapp peaks, can you determine how large the lattice is based on where the Umklapp peak resonance occurs? On
yes, thank you. That's exactly true. So that's what I was plotting here. So basically, this is the green circles are the energy of the Umklapp resonance as measured from the exciton resonance at that density. So this is gate voltage or the electron density. So what we plot is the energy of the Umklapp as measured from the exciton as a function of the electron density. And indeed, this blue shift is determined by the electron density and the mass of the exciton, nothing else. And of course, also the lattice structure, but this we assume to be a triangular lattice, which is what you would expect as the most, let's say, energetically favorable configuration. So in it, maybe I say a bit more there. Normally you could say that if you have a lattice, the way you normally characterize lattices is to use X-rays and do Bragg scattering, right? So but then you would need to use an incoming photon whose momentum matches the lattice momentum, or the wavelength matches the separation between the elements, atoms, or electrons in the crystal. So, but X-rays do not interact strongly with electrons, actually very weakly, particularly if you have a single layer, it's practically impossible to see this. So the trick here is that we use excitons. Excitons can be generated at k equals 0 with optical photons, but because what you generate is a massive particle, finite momentum excitons can actually have a very small de Broglie wavelength. This de Broglie wavelength could actually match match the lattice separation, and in this way allow us to sense the periodic ordering. I don't know if that helped, but I thought I mentioned.
Yeah, that was really informative. Thanks.
Would anyone else like to raise their hands? If not, maybe I'll ask. So I don't know, in like the condensed matter kind of lore, there's like sort of localization effects happening if you have, like if you add disorder to the mix. So like, how does that, like I'd imagine if you make the Scotch tape, you have some amount of disorder, but.
Yeah. That's an excellent question. Of course, there is disorder, and that's why this Umklapp resonance is as broad as it is. Basically, we actually use measurements at finite magnetic field to characterize the effect of disorder. And the main effect of it is that it limits the size of the perfect crystal. So we should really say that, or I should have said that we have a sample that is a few microns in size. The Wigner crystal doesn't extend as a single pure crystal over this whole area. We have Wigner crystallites of size on the order of 100 nanometers or so. And this actually we determined with help of, mainly through our collaboration with Eugene and Pavel, his PhD student Pavel. So this was a very important element or part for us that we can actually use the Umklapp resonance at finite magnetic field, though, because we need to tune it closer in resonance to the exciton. But then we can use its line broadening to extract the information about the disorder in the system, and it is there.
I guess my question is, does it help stabilize the Wigner crystal phase, or like, what is the way to think about that?
Yeah. So I believe that at finite magnetic fields, at least, that this is the case. So basically, if you go to, let's say, finite magnetic fields, or you can say even high magnetic fields, there are, let's say, competing states in the system. So one of them, a very prominent state is the integer quantum Hall state. Then if the material is clean, then the fractional quantum Hall state. So these are liquid states that are let's say, rather robust and play a prominent role. Now, Wigner crystal competes with these liquid states in finite magnetic field, and disorder appears to have, disorder is known to be an enemy of fractional quantum Hall state. So I believe, and want to be tentative here, but I believe that we are really using disorder, at least at finite magnetic field, to our benefit in sort of seeing Wigner crystal states. With integer quantum Hall at very high fields, it dominates. So we no longer have Wigner crystal, but rather the integer quantum Hall states. In the absence of magnetic field, whether disorder really helps the Wigner crystal formation, this I'm not sure. I don't think so, but yeah, I'm not sure. So I shouldn't say more.
Okay, thanks. Garrett, go ahead.
Hello, Professor. Great talk. It was really fun to listen to. So I actually had a question more on the actual fabrication step. So the lab that I work in here at the University of Minnesota also does 2D structures. And we've been experimenting with different types of tape. Have you actually tried using different types of tape other than Scotch tape? And have you had any success with that, or?
Yeah, so I believe that the what we are using is what my students describe as the blue tape. Honestly, I'm not sure sort of what the distinction is in terms of the material or the sticking material as compared to the sort of over-the-counter Scotch tape is. But so there is a difference between different kinds of tapes, but deep down it is still the same technique, and that's all I could say. As I told you, I mean, I've done exfoliating myself, but this was only once. So so all these devices were fabricated by my students. What is really nice then, as you would know, since you know in such a lab, is that it's so easy to access this growth, right? I mean, previously when we were working with gallium arsenide, we had to request that the material was grown for us in an MB machine. Here, it's basically we have our own facility, and it's much easier to fabricate. But I can tell you more. So I believe that I'm pretty sure we don't use the regular Scotch tape, but the distinction between the two, and I can't really say more.
Yeah, it's funny you say it. I was wondering if it was going to be that, because I know a lot of places use the blue tape. So yeah, all right. Thank you.
And Professor, if you have just a minute for one more question, there's another one in the audience.
Sure. Yeah.
Awesome. Yeah. So just
There are 2 more questions, but then we'll let you go. It is 11:30 for the guys, so
that's okay. Don't worry.
Zhu, if you want to go ahead and ask your question.
I'm in the lab. Can you hear me?
Yep.
Okay. Hi, Professor.
Hi.
I saw that your current direction is very different from what you did in your PhD. I was just wondering, in general, how do you decide which direction to pursue and what research directions are interesting and important?
Yeah. So
actually, I could interject really quickly. The second question is also similar, so maybe you can kind of parallelize.
Okay. Should I listen to it first? Or?
Yeah. Sorry, give me a second. Yeah. I had to figure out how to unmute after a year of using Zoom. And the second thing is, would you please tell us a bit more about your future in this field of research for the next 5 years, and if your future directions will be more fundamental or applied? So yeah, maybe these are somewhat related questions.
Yeah, so again, this is sort of one hint that I got from my PhD supervisor, Steve Harris, whom I have the highest respect for. So Steve basically changed his research topic more or less every 5 years. And he was always working with laser and atomic physics, but really changed his focus onto different questions. So I thought that this was really cool and refreshing. So I tried to do that myself. And I mean, starting from postdoc years, but basically for a time period, I was interested in single photon sources, then spin qubits. Then I thought that it would be very nice to use what we have learned to study many body physics. So that's how I got into Kondo effect. And now really the sort of investigation of strongly correlated systems. So, yeah, I mean, I guess overall I see myself more moving in the direction of more fundamental physics over my career, and I'd like to keep changing the topic as well, or the material system of interest if possible. But I should also say that in condensed matter physics, there is always some application sort of in the background, right? So for example, one of the questions I'm interested in is whether I could use the interaction between excitons and electrons to realize a superconductor, to induce superconductivity in the semiconductor material by applying a resonant laser that is converted into excitons. So you see that I mean, this would be, again, in my opinion, a very cool experiment to control superconductivity using optical means. But in the end, there would be a device, if you will. So in that sense, I'm not sure if I should call this more fundamental physics because applications are always sort of in the background. But it is true that on the other hand, that I'm interested in, more and more interested in trying to understand not only, let's say, superconductivity or how to induce superconductivity, but for understanding more exotic systems or exotic physics.
Thank you very much.
All right. If you have time for one more question, and then I think, guys, no more questions after this ever.
Okay, sounds good.
Ingi, go ahead. Or Ingi, go ahead.
Oh, it's Ingi.
Oh my God, sorry.
No, it's fine. Everybody mispronounced it. It's fine. I was going to ask, like, how does one change their research topic so easily? Like, is it easy to do that? How does one go about it?
Yeah, that's an excellent question. So you need to have a handle. I mean, it's really not, I don't think it's possible, at least not for me, to basically sort of stop doing the kind of physics I'm doing now and be productive in astrophysics. You know, so what I learned again from my supervisor is that you know, in doing research, you develop some tools, you understand certain physical phenomena, and then you want to be able to make use of this in another topic. So that allows you, that gives you an advantage in when you venture into a new field, because you bring with yourself a tool or a good understanding of physics, of your tool, let's say, and then nevertheless it also gives you an open mind about a new field. People have thought about it, and so there are many people who know a lot more about this than you do, which is also very good because you can learn from them. But you also start with the more open mind. So you're sometimes working in a field for a very long time could actually hinder your productivity, because you may not be able to think as freely as you would if you were a bit naive in your approach to the system. Does that help? Or
Yeah, thank you.
Yeah.
I also really enjoyed your talk, so thank you for taking the time.
Thank you. Yeah. Okay.
So yeah, so I wanted to thank you again, Professor Imamoglu, for an excellent conversation today. It was
a
really
pleasure.
Yeah. It was a pleasure to hear about your career and your current research interests. And for the next few weeks of Quantum Summer, we have a really exciting lineup of speakers for those in the audience still here, including Emmanuel Bloch of Max Planck, Michel Devereux of Yale, Junior of CU Boulder, Monica Schleier-Smith of Stanford, and many more. And I hope to see you all at those talks in the next few weeks. And once more, thank you so much, Professor Imamoglu, for the
You're most welcome.
conversation.
Thank you. Bye.
Goodbye.
You want to stop recording?